So I'm very happy today to introduce Lindsay Sanneman from Massachusetts Institute of Technology. Lindsay is a postdoctoral associate in the Department of Aeronautics and Astronautics at MIT and a member of the Interactive Robotics Group and the Algorithmic Alignment Group in the Computer Science and Artificial Intelligence Laboratory. Her research focuses on the development of models and metrics and algorithms for explainable AI and the AI alignment in complex human autonomy interaction settings. Since 2018, she has been a member of the MIT Work of the Future Task Force and has visited over 50 factories worldwide alongside an interdisciplinary team of social scientists and engineers in order to study the adoption of robotics in manufacturing. She has been a Siegel Research Fellow and has presented her work in diverse venues, including the Industry Studies Association and the Federal Aviation Administration, and the UN Department of Economic and Social Affairs. So I'll give the floor to Lindsay.
Thank you so much, Sylvia. It's really great to be here with you all today. So I'm really excited to be here and to talk to you today a little bit about my primarily my thesis work and now my postdoctoral work at MIT on transparent value alignment and foundations for human-centered explainable AI in alignment. There we go. So throughout my research, I've been really fortunate to have the opportunity to visit a number of real-world domains that have great potential for new human-robot interaction applications. So, for example, I spent time at NASA JPL observing the tactical planning processes for the Mars rover. And then separately, through the work of the Future Task Force, I've gotten to visit a lot of factories to look at how new robotics and AI technologies are being adopted in manufacturing. And so when I went out to these domains, what I thought and hoped I might see was something like this, with highly automated planning and scheduling at NASA, and many new HRI applications and robots overall in the factories that we visited. But instead, what I saw was something much more like this, with primarily manual scheduling with many hours of meetings between scientists and engineers at NASA, and very outdated equipment with almost no robots at all in the factories we visited. And so the question was, where are the robots and automation? Well, when we asked about this in these various contexts, we actually heard a pretty unified set of answers. And this was that robotics and automation in their current form are too opaque and unpredictable, so we can't trust them to help us with our tasks. They're too inflexible and single purpose. And they're too difficult to program, especially for people who aren't programming experts. So then we know that in order to lower the barrier to use of these systems, we'll need to make them more transparent and have them foster appropriate trust, make them more flexible, and easier to use. But even with the current limitations that we heard about in our interviews in these various domains, we did actually see a few successful applications of HRI solutions. And one in particular was at a company in Germany that manufactures power equipment. And here we saw an amazing HRI application where this large robot arm, which the workers called the Green Hulk, worked side by side with a line worker to lift, test, and package various types of heavy power equipment. And so what we learned over the course of our interviews was that companies that had successful applications like this had almost always put workers at the center of the solution development process, both drawing on their deep domain expertise, but also asking what their needs were in terms of what would make their jobs better. So then, in addition to making systems that are transparent, flexible, and easy to use, we know that it's critical to put humans at the center of the solution development process if we want our solutions to be effective. So the next question is how we can actually do this. So to think about this, we can start by thinking about how we might model a person's expertise and goals that they might have for a robot, and what actually makes doing this a hard problem. So one common way to represent objectives like this in robotic settings is through reward functions. And so here we'll call the human's reward function RH. And so reward functions often represent goals in terms of a set of important features and weights, which indicate their trade-offs. And so they're really a convenient way to represent desirable and undesirable agent behaviors in settings like reinforcement learning, for example. So then the question is, why can't the human just give their reward function directly to the robot or agent to help them with their tasks? Well, it turns out that this is really hard to do well. And there's literature that suggests that this is even hard for reinforcement learning experts. So to see an example of how this might be hard, imagine we want to take our green Hulk robot and repurpose it to help us palletize boxes that were just packed from the assembly line. So here we'll assume that the robot knows how to pick up boxes from the conveyor belt and pack them onto the pallets, and the goal is to pack as many pallets as possible. So the human, with this goal in mind, gives the robot one reward feature for stacked boxes with a weight of 1. So in other words, 1 point is awarded for every successfully stacked box. So given this reward function, the robot starts to pack boxes onto the pallet. But now imagine that the conveyor belt runs out of boxes. Well, with the reward specified as it is, the robot might start to unpack boxes back onto the conveyor belt so that it can repack them onto the pallet to maximize the overall number of stacked boxes total. And so this is clearly undesirable. And this is an example of what we would call reward hacking, or in other words, unexpected behavior or loophole exploitation that might happen due to reward misspecification. So the human sees this, realizes they forgot to penalize unstacking boxes from the pallets, and adds a feature to penalize this in the reward function, and we're all set. So this is a pretty simple example, but in a real factory environment or anywhere else where this might apply, there are likely many more factors that we must account for. So this can be really hard, but it's also expensive or even dangerous sometimes to get it wrong. So to deal with this, there have been a number of approaches proposed for inferring human rewards from different types of input, like language or preferences or demonstrations, for example. And so we call this process reward learning. And this process of aligning a robot's goals with a human's via reward or any other representation has more broadly been called value alignment in the recent literature, since it's fundamentally about learning how a robot should behave in order to act in line with what humans value across these various contexts. So the key insight of my work is that this alignment process is really a two-way street, and that directly and explicitly explaining a system's current representation of its values and goals to humans is really a critical aspect of making the overall alignment process more efficient and effective. And so I call this two-way communication process transparent value alignment. And so my research to date has focused specifically on this explanation part of the problem, and in particular looked at how to align human understanding of AI systems through approaches for explainable AI. So what do we actually need to be able to do this? So my research has looked at 3 questions on this front. First, what it means to be aligned and how we can quantify and measure alignment. Second, what information explanation should explain to people and how it should share this information, both in the alignment context, but also more broadly. And finally, how we can actually use the answers to these questions to generate effective explanations through mathematical modeling of design trade-offs. And so, and then beyond this, in my research, I've also looked at how new technologies can be effectively and responsibly applied in the real world through a variety of projects in industrial robotics and medical AI. And some of the findings from all of these projects really highlighted the critical need for AI transparency in real world implementation of these systems. And so this work really addresses those critical needs as well. So I'll start by talking about what it means to be aligned and how we can actually quantify and measure it. And this is really a challenging problem because we don't necessarily have direct access to the latent set of values or goals in the human's brain. So to start, as we saw before, the problem of alignment is often formulated as a problem of reward learning in the literature. So here we assume that there's some latent human reward function, which the robot can infer through interactions. So for example, either through direct reward design by the human, through human preferences or demonstrations, and there are a variety of other possibilities as well. And so all of these approaches essentially assume that some causal model like this exists, where the latent human reward influences how the human produces these different types of inputs. And then most also make a noisy rational assumption about the human. In other words, that the inputs are produced somewhat imperfectly. So then for evaluation, many of these works have also assumed access to a simulated ground truth human to compare against the learned reward. And so this works great when we have access to this ground truth. But what about when we don't? And in the real world, we won't. And humans might also violate the noisy rational assumption, or we might not have ready access to the ground truth set of reward features, which is another common assumption these works make. But even in these cases, we need a way to be able to rigorously and effectively assess alignment. So how can we actually do this? Well, one approach that's commonly applied in cognitive psychology in order to validate scales for things like depression, for example, is called structural equation modeling, and in particular, factor analysis. And so this basically involves validating that a proposed causal model like this one is a good model for the data we're able to measure, or our observed variables, in other words. So we can also apply this to alignment. So here in thinking about how to do this, we'll focus on these three types of human input in particular. But now instead of measuring reward directly, we're instead interested in measuring alignment. So essentially, we want to look at the distance or similarity between the humans and robots' rewards. So based on this, we proposed 4 metrics for reward alignment, which capture this similarity. And these 3 metrics, again, draw on these 3 types of human input about rewards. And then we also validated these metrics through the structural equation modeling approach I mentioned before. So I'll give a very brief overview of each of these metrics and then the validation process as well. So here, again, we assume that we have human and robot rewards, which are functions of some set of features and weights. And so, again, I won't go into depth about how the metrics are calculated, but as a brief high-level overview, the direct reward design-based metrics are both intersection over union metrics, which capture the similarity between the humans and robots' features and their relative weights. And the difference between these is how we collect data from the human, either in free form or in the feature subselection case, humans select features from a preset list. So the preference elicitation metric looks at the overlap between human and robot responses to a set of preference queries. And then finally, the best demonstration metric is a regret-based metric which compares optimal human and robot demonstrations in terms of their reward values. So in order to validate these metrics, we ran a human subject experiment and applied the structural equation modeling approach for validation, which I mentioned before. And in the experiment, we leveraged a grid world environment with ground truth reward functions like the one here with various colors and weights. And then throughout the experiment, we varied participant alignment with this ground truth by providing either full information about the reward or partial information with weights or entire features missing. So then for each scenario, participants responded to each of our 4 assessment questions. And from this, we were able to calculate our metrics, which should capture this variable alignment. So the structural equation modeling process involves multiple steps, which draw on processes like dimensionality reduction in order to uncover underlying structure within the data. And so I won't go into detail about these steps, but the following causal structure with these 2 primary latent factors emerged from this initial process. And so we actually gave these factors names. The first we called feature alignment, since the 2 metrics associated with it assess alignment by asking people about feature-based reward information directly. And then the second we call policy alignment, since its metrics assess policies or behaviors that correspond to a particular reward function. So our initial question here, though, is about alignment overall. So in order to look at this, we followed this analysis up with what's called a second-order formative factor analysis, to look at whether some higher level latent construct, which we'll call overall reward alignment, was also supported by our data. So in the second order analysis, which we performed through a partial least squares approach, we found the factor loadings, path weights, and Cronbach's alpha values that you can see here on the slide. And so these values meet a set of common criteria for model validity in second order analyses from the literature. But what does this actually mean? Well, this is a powerful result because this means that we have now validated our proposed set of metrics for alignment through human subject experiments. And we've also uncovered this underlying structure, which tells us that there are actually at least two different components of alignment that exist, which we can study either on their own or together in our future research on alignment. So to cap up this work, here we started with this question of what it means to be aligned. And we uncovered this underlying structure that exists and how we can actually characterize alignment. And we now also have the first set of metrics for alignment, which have been validated through human subjects experiments. And so this will really enable more rigorous and human-centered alignment research in the future. And then this can also be used as a launching point. So any newly proposed metrics in the future for alignment can also be validated against this existing set. Okay, so now that we have these metrics, we can apply them to actually analyze alignment, including the explanation part of the two-way communication process I talked about before. So next, we'll dig into this question of what explanation should explain and how they can most effectively communicate this information, which is really one of the central questions of explainable AI. But it's also a really challenging question because one size does not fit all when it comes to which information people need, given their different roles and contexts. And there are also design trade-offs that exist in explanation development. So here, first, I'll talk about a framework that we introduced and then a subsequent set of studies we performed, which build on the field of human factors and leverage our validated metrics to answer this question of what and how explanation should explain. So here we'll start by considering the concept of situation awareness from human factors. And so this is a construct that basically states that people need to be able to perceive, comprehend, and project the status of elements in the environment that relate to their tasks in order to actually perform these tasks successfully. So we can also use this as a launching point to think about how XAI systems can be applied to meet human informational needs. So based on this, we propose the Situation Awareness Framework for Explainable AI, or SAFE-AI. And this framework enables us to systematically determine what information an agent needs to explain about itself in order to support humans with their tasks in any given scenario. So as a brief high-level overview of this framework, Level 1 explanations answer what questions about an agent. Level 2 questions answer why or how questions and give information about causality in decision-making. And Level 3 explanations answer what-if questions and incorporate counterfactual or contrastive information. So there are more details on this framework in the references on this slide, but one thing I want to highlight here that's really central is that information at these three levels is highly context dependent. It depends on the person's role, their task, and their expertise, among other things. So these levels will look different for a robot programmer than a line worker in the manufacturing setting, for example. So then for any given scenario, SAFE-AI enables us to comprehensively enumerate a person's informational needs according to the three levels of the framework we just saw. And then identify existing explainable AI techniques that can be applied to meet these needs. And where such techniques do not yet exist, it can also help us to identify gaps in the state of the art and corresponding areas for potential future research. And finally, there are existing evaluations for situation awareness from the human factors literature, which can be applied to rigorously evaluate explanation quality. Okay, so situation awareness helps us to determine what explanation should explain. And then the human factors construct of cognitive workload can help inform how much information explanation should provide and at what frequency. And this is based on human cognitive capacities. And so we'll look at this a little bit more next. But then beyond these two, trust is another critical factor to consider. And so to date, much of the XAI literature is really focused on using XAI to increase trust. But human factors has instead emphasized the importance of calibrating a person's trust to a system's capabilities in order to facilitate appropriate use and reliance on these systems. And so this also has important implications for the design of XAI systems in the future. But next, we're going to focus in on situation awareness and workload in particular, and how these are actually traded off in explanation design. And so in order to look at this, we performed an experiment comparing a broad range of explanation techniques, and we studied these two human factors constructs for these explanations. So to get into this a little bit, as we've seen, reward information is really central in the alignment setting. And so here we're studying explanations of reward functions in particular. And there are a variety of approaches for doing this in the literature, and 4 of the most common modes of these explanations are the ones here on this slide. So these include feature importance techniques, which highlight the most important features for decision-making, reward abstractions, which explain high-level abstractions of low-level reward features to users, policy summaries, which show optimal policy rollouts from diverse regions of the state space for a particular reward function. And finally, factored policy techniques, which present users with information about ideal actions, along with information about the importance of various reward components for each of these potential actions or decisions. So if we look at these techniques, we might notice that they broadly fall into 2 categories, which map closely to the components of reward alignment, which we identified in the metric validation work. And so one of these we'll call feature-based explanations, which explain reward in terms of features and their relative weights. And the other we'll call policy-based explanations, which explain reward in terms of behaviors or policies that correspond to a particular reward function. So between all of these approaches, so far these techniques have typically either been studied in isolation or compared with a single other approach. And there have really been a limited set of human-based studies looking at these techniques overall. So in order to fill this gap, we selected one of the most widely cited or applied techniques from each category to compare against the others. And we did this through human subjects experiments that studied the human factors constructs that I talked about before. So in addition to these 4 techniques, we also implemented baselines for each of our feature and policy space categories. On the feature space side, we showed participants the entire reward function directly in bar graph form. And on the policy space side, we showed participants the most and least optimal trajectories or best and worst demonstrations for the particular reward function that we were studying. We implemented these 6 explanation techniques across 2 domains. These included first the threats and waypoints domain, and this had agent navigation requirements, which were encoded as linear temporal logic specifications, which were converted into a reward machine formulation. And then we also had a grid world domain where differently weighted colored grid squares were penalized or rewarded differently. We also considered 2 levels of reward complexity, where complexity was defined as the number of features in our linear reward function. And so each explanation technique complexity pair was compared with all others via within subjects experiments in each domain here. We measured 3 dependent variables in our experiments, both objective and subjective. And so for the objective assessment, we measured reward alignment, or as we'll call it here, reward understanding. And we did this by applying the 4 validated metrics that I discussed in the previous section. And here we combine them into a single composite metric, which sum them together. And so this is effectively our measure of situation awareness or understanding in this case. For our subjective assessments, we measured cognitive workload through the commonly applied NASA TLX scale, and also participants' subjective assessment of the explanations through a scale for team fluency. For our data analysis, we applied linear mixed effects models of the following form in standard Wilkinson notation, and we looked at complexity and explanation type as fixed effects, as well as their interaction effects here. But I'll dive into the results for complexity and explanation type a little bit more in particular. So in comparing explanations across the two levels of complexity in our experiment, both low and high complexity, we found significant main effects across both domains, which indicated that understanding worsened with high complexity rewards, cognitive workload increased, and subjective assessment of the explanations worsened in the threats and waypoints domain in particular. So these decrements in understanding and subjective assessment and increases in workload really tell us that we need to be mindful of the impact of complexity on explanation efficacy in the future. And so next, in comparing explanation techniques directly with each other through post-hoc Tukey's HSD pairwise comparisons, some of the key takeaways were first, that providing the full reward function directly to participants corresponded to the best understanding of all techniques where we saw significant results. But this also came at a cost. It was also associated with higher workload than all other techniques, along with the policy summary and factored policy techniques, which also provided full or near full information about the reward to participants. So together, these results really suggest a trade-off between understanding and workload when full or near full reward information is available to users. There was, however, a promising way of addressing this trade-off that emerged, and this was that the reward abstraction approach struck a nice balance between all of these factors. It corresponded to better understanding than all other techniques besides the direct approach, as well as lower workload and better subjective assessment than all other techniques. So this is especially promising to apply for future implementation of explanations, especially as reward complexity increases. So since the abstraction approach was successful, to get a quick sense of what this looks like, we can look at a quick example in the grid world domain. So here, let's say we have a grid with 5 different colors that are shades of blue, purple, and orange. So in this case, our direct approach might look something like this with the various colors and their weights. And then the abstraction in this case would look like this, where the shades of each color are grouped together and presented to users as single abstract features. So when we say abstraction, something like this is what we mean. So after our initial experiments, we also ran a follow-up experiment, which included a secondary distractor task, which involved participants monitoring a robot navigating in rocky terrain through a video like this. And here we were looking at whether the results were impacted by the addition of this extra task and workload. And so in this experiment, we studied the direct and best and worst demonstration explanations. In other words, our baseline feature and policy space techniques. And we found results that were consistent with those in the original experiment. In other words, that the direct explanations, which provide full reward information, corresponded to improved understanding, but also higher workload than the best and worst demonstration approach, even with this extra distractor task included. So we again see the understanding workload trade-off emerge here in this experiment. Okay, to summarize this work, here we were looking at this question of what and how explanations should explain information to people. And to address this, we proposed a human factors-based transparency framework, and we performed human subject experiments to study reward explanations along a variety of human factors dimensions. And so I'm really excited about this work because this framework represents a formal bridge between the algorithmic XAI and the human factors communities. And what I hope is that this will enable a rigorous and enhanced and human-centered approach to design and evaluation of XAI in the future in a way that hasn't been possible before. And then in addition to this, these experiments were actually the first set of extensive human studies comparing a broad range of reward explanation techniques. And they provided us with some initial design guidance for explanations. And this was that there's this trade-off between understanding and workload that we must consider in explanation implementation, but also that reward abstractions might be particularly effective for striking a balance between these factors. Okay, so last, we've seen that abstractions can help to balance understanding and workload, and so far we've really primarily considered handcrafted abstractions in our analysis. But ultimately, it would also be useful to be able to automatically generate these explanations. So to this end, in this last part of the work, what we were exploring was whether we could automatically generate explanations that effectively trade off workload and understanding in a way that's also tailored to individual user informational needs and cognitive capacities. And the main challenge here is really being able to mathematically model the human factors that we need to trade off in explanation generation. So we can look to information theory to help us with this task. Okay, so in information theory, the information bottleneck is a method of lossy compression where some input concept X is passed through an encoder, which then outputs a compressed latent representation of the input C, which gets passed through a decoder, which reconstructs the input as well as possible. And the reconstructed input is represented by X hat here. So in training this encoder-decoder setup, the goal is really to compress the inputs into C in a way that maintains as much information about the inputs as possible. So in this work, we were looking at whether we could leverage this information bottleneck model in order to also model explanations. And specifically here, we treat the explainable AI agent as the encoder, which communicates some compressed information to the human with the size depending on the human's cognitive load. And then we treat the human as the decoder who receives this compressed information and tries to interpret what the agent was communicating as well as possible. And so the explanations here are represented by the latent representation C. So to formalize this a bit more, when we train these latent representations, we want to trade off minimizing the complexity of C and maximizing its informativeness. And so here we define complexity as the mutual information between the input and the compressed representation, or in other words, the KL divergence between C conditioned on the input and C itself. And then informativeness is captured by the inverse of the distortion here, which is defined as the mean squared error loss between the original input and the reconstructed input. And so our key insight is that when we treat the compressed representation C as explanations, there are potentially connections between these information theoretic optimization criteria and the human factors constructs, which we looked at before. And so specifically, we hypothesized that for a given explanation presented to a human, complexity would correlate with human workload, and informativeness would correlate with human understanding. And so the goal here was really that if we can demonstrate these connections empirically, then these information theoretic terms can actually be used to model the understanding workload trade-off we identified in the previous experiment. So here we set out to establish those correlations empirically through human subject experiments. And again, we were looking at explaining reward functions here, and we did this by looking at reconstructing a reward function from the latent representation rather than the original input. And you can see that depicted in the upper right here. And so we performed experiments across two domains, one that involved navigation through a grid that had differently valued grid squares, and one that involved differently valued color swatches. And so in each case, the information theoretic algorithm automatically abstracted the input space into a discrete set of reward regions C, like you can see here, where each color in these heat maps was associated with a different reward value. And so then we showed these abstract regions to participants and asked them to answer questions related to their reward understanding as well as their workload. So for each participant, or for each scenario, each participant was shown a reward function that varied continuously in the input space, like this one here, which varied as a function of distance from the particular one particular square. And we also showed them rewards that varied discontinuously. For example, like this one with randomly assigned reward values here. So we also showed participants various levels of abstraction complexity with different numbers of reward regions. So for example, you can see 2 or 3 regions on the right, as opposed to the 6 or 7 in the highly complex cases on the left. And these were trained by trading off the weighting parameter between complexity and informativeness differently, and more highly penalizing complexity. So for each explanation and level of complexity, we again leveraged 2 of our validated metrics to measure understanding: feature subselection from the feature alignment category and best demonstration from the policy alignment category, and looked at how these understanding metrics correlated with informativeness or distortion. And we also measured workload through the TLX scale and looked at how this correlated with the complexity of the explanation. So to look at our results, we'll first look at feature understanding versus informativeness or distortion. And here, since we consider distortion to be the inverse of informativeness, what we hope to see are negative correlations between understanding and distortion, since we expect informativeness to correlate with understanding. And so that's what we see. For both types of reward functions across both domains, we saw significant negative Spearman correlations with stronger correlations in the grid navigation than the domain than the color domain. And so one possible reason we saw stronger correlations for the navigation domain was that visualizations in the color domain required an extra step to interpret, which involved moving from reasoning about individual colors to the task space, while the grid navigation abstractions, on the other hand, were provided directly in the task space, which was just the grid itself. So we also see similar results reflected in the policy understanding and informativeness results. Here we saw significant correlations in the grid navigation domain only. And then finally, when we looked at workload versus complexity, we expect to see positive correlations because we expect higher complexity to be associated with higher workload. And so here we see positive trends for each case, but only one significant correlation for the discontinuous grid navigation reward in particular. And so one possible reason for the lack of significance here could be that the individual differences in participant responses to the subjective TLX workload questions caused variability in the results. And so we dug into this a bit more and performed a follow-up analysis, which leveraged the fact that each participant saw both a continuous and discontinuous reward within the given domain. And so we were actually able to combine the continuous and discontinuous data in a way that controlled for these individual differences. So we performed this follow-up analysis through linear mixed effects modeling. And when we did this, we found significant main effects for distortion in our feature understanding models across both domains, as well as for policy understanding in the grid navigation domain, and also for complexity in our workload models across both domains. And so these results provide support for our hypothesized correlations, and particularly for the feature understanding and informativeness and workload and complexity correlations that we hypothesized. Okay, so to sum this up, here we started with this question of how we can automatically generate abstract explanations. And to address this, we proposed an information theoretic model which can be applied to trade off workload and understanding in abstract explanation generation. We also established empirical connections between understanding and informativeness and workload and complexity through human subject experiments. And so the really exciting thing about this work to me is that because we have established these connections, we can now use this model and this approach to automatically generate user-tailored abstract explanations that trade off these human factors constructs effectively. So I'm really excited to apply this approach more broadly in the future and to study it across more domains too. Okay, so before I wrap up, I want to very briefly give a sneak peek of some of our next directions, which I'm currently working on. So we've talked a lot about aligning reward functions for robotics today, but rewards also have applicability beyond this. For example, for applications like reinforcement learning from human feedback, or RLHF, from in the large language model setting. And so here, human preference data is used to train a reward model, which is used to fine-tune language models to perform particular tasks. So one of the things I'm looking at right now in collaboration with Professor Dylan Hadfield-Manel is whether we can actually explain these RLHF reward models to people and whether this improves people's alignment or their understanding of large language models overall. And then in conjunction with this, I've also been exploring whether we can enable humans to co-create abstractions for bidirectional communication with these systems, rather than having these abstractions be entirely hand-defined on the one hand, or completely automatically generated on the other. And the hope is that this will enable both effective explainability, but also more efficient generalization to new domains on the computational side of things as well. So I'm excited to continue this in the coming months and to start to get some results on this work. All right, I want to take a moment to thank my amazing collaborators. This work would not have been possible without this amazing group of people. And I'll finish up by leaving some of the key takeaways from the talk on this slide. And I'm very happy to take any questions you might have about this work. Thank you very much.
I was wondering if you could comment on like the frequency of an explanation, so rather than like what and how, like when an explanation could be delivered. Or which of your works like kind of touch on that, and what are your thoughts about that?
Yeah, so that's a great question. So yeah, as I had mentioned, I think what you're pointing at is workload can inform both like how much information an explanation can provide. And we looked at that a little bit with our experiments, looking at complexity, like how many features can we explain and what's the impact on workload. But there's also sort of this higher level factor of at what frequency can this information be provided. And so our experiments so far haven't looked at that question as much yet. It's something I'm hoping to explore in the future. But our Safe AI work actually talks about different models from human factors that we might leverage in thinking about how to design for these considerations. So we call the how much information consideration local workload, and the at what frequency global workload. And so there are models from human factors, one called the multiple resource model, which sort of groups human cognitive capacities into different buckets. And so what we'll need to do is consider the full set of tasks that the human is performing when they receive an explanation and say, okay, so here's how much of each modality of information they're receiving and where the explanation fits in. And based on this, we can start to think about at what frequency can we provide these explanations. But definitely more space for experimental research with explanations in the future on this front too.
Well, thank you. That's a good answer.
So great talk. And I was just wondering if you had thought about human robot interaction and explainable AI being applied to different contexts other than maybe like industry or factory robots. So for example, maybe it can be applied to like home settings or like other workplaces that use robots. I was wondering if you had any interest or thoughts on that part.
Yeah, absolutely. So you're right. I've looked at factory settings a lot, and also sort of the NASA context. But my hope is that some of our work, like the work we did on developing the framework, has more broad applicability. And one of sort of the key points of that work is really that explanations need to be very user-tailored and context-dependent. So to figure out what we should explain and how, we actually need to talk to subject matter experts in these domains and say, what information do you need? What like XAI techniques do we have available in our repertoire to apply? in order to meet these needs and to do this in a very user-specific way. So the framework provides some guidance for doing that. And I'm actually looking at applying this in like a mission operations domain for the Army right now as well. There are also Air Force pilots I've been in communication with who have interest in looking at explainability requirements for automated fighter jet piloting, basically. And so I'm hoping to look at it in those contexts in addition to applying it also in the industrial robotics setting. And I think like home robotics is another great application where home-based users might not necessarily have any expertise at all in robots and their models and how they operate. So that would unveil hopefully a whole different set of requirements and tell us if we don't have explainability techniques that can meet those people's needs, where do we need to push the boundary in research next?
Awesome. Cool. Thanks, Lindsay, for such an amazing talk and really, really cool work across many different levels, high level experimental results, metrics, etc. One question that I had was, I really like the categorization between feature-based methods and policy-based methods, and it seems very, very intuitive. And I'm wondering, have you come across work that actually are kind of like a hybrid of the two? Because some, like my work, for example, I'm coming up with demonstrations that are explicitly geared towards actually trying to enumerate the different feature weights. So it's kind of like, it kind of sits in between those two methods. And I'm wondering if you've seen other work that are also kind of hybrids. And so like, what are the strengths and weaknesses of that, I guess?
Yeah, absolutely. And yeah, I'm familiar with your work, Mike. And I think, yeah, this is a great example. And I have definitely seen other examples of a hybrid between these two. Here we were trying to sort of do a first pass analysis of like each bit of information in isolation. How effective is it? What are the trade-offs? But I definitely think that looking at combinations of these different techniques could support better understanding overall in the future. And in fact, in some of the RLHF explanation work we're looking at now, we're thinking about how can we augment examples with like reward values, for example, to give a more comprehensive overview of what's going on. Some of the factored policy techniques that I cited on the slide also have sort of looked at combinations of policy rollouts and reward values for different actions together in combination. So I think there's definitely work in this space, and the trade-off that might exist is in the complexity of the information that's presented to the human. So one thing we would probably want to be careful of is how much information the person is actually required to process and whether they can actually do this effectively. And so I'm very encouraged that there's great promise for looking at hybrid approaches in the future, and would hope to look at some of like the workload trade-offs that might exist there in studying those techniques too.
It's a really good answer. Actually, based off of your results, that suggests that direct reward explanations are better at yielding both objective and subjective results. I'm actually following up and doing another study that actually shows both reward weights and demonstrations, so I can keep you posted on what those results are as well.
Oh yeah, please do. I've been following your work. I'd love to, love to keep in touch about that.
And I guess a quick follow-up after that is, are you aware of work that have explicitly looked at showing like different types of explanations, be it feature or demonstrations in sequence? Because I know that like maybe like policy summaries are more global, so maybe you can start off with that, and then once you are able to identify gaps in understanding, maybe you can go more local with the feature-based explanations. I'm not aware of any, to be honest.
Yeah, this is a good point too. And I think there's a lot of literature in like curriculum-based approaches, which Brad Hayes from CU Boulder, I know, has looked at a little bit that might sort of address this. And there's also a lot of research in cognitive psychology on like curriculum-based approaches for teaching people about different concepts. And so I think there might be connections here in the curriculum space to start exploring how might we present this information in sequence in the most effective manner to build up human understanding over time too. So this temporal aspect is a really exciting future area to research too, I think.
Yeah, I totally agree with that. Yeah, I've been casting most of my work in the framework of zone of proximal development / scaffolding. So that's really similar to to curriculum learning. So I think that it's like very neighboring area.
Yeah, awesome. Yeah, thanks for the pointer to that.
Yeah, thanks so much for the answers, and definitely we'll keep in touch.
Yeah, please do.
So thanks once again, Lindsay. And it was really, really great to have you explain those things, because many things I've read or like seen in your paper seem it much more clear now that I had you explaining them. And so thanks a lot for your talk.